So we have almost done with the fluid mechanics part, okay, where we learned how to calculate essentially pressure drop, and the whole idea was to get the right pump that is suitable. Now, but as we saw in the beginning of the course, okay, this fluid flow is not just confined to analysis of pipe flow. There are several situations, I mean, in almost every place that you look at, fluid flow becomes important, okay. So there are many more things that need to be done. And as a chemical engineer, one of the context in which again fluid flow will become important is in the context of boundary layers. So that's what we are going to start looking at from today onwards. So boundary layer is nothing but the region of the fluid flow that's affected by a nearby solid boundary. Okay, so for example, if you have a flat plate, let's say a solid plate, and if there is a fluid that's on top of it that's flowing, there will be a region, okay, which is affected by the solid plate. And then there will be a free stream that's outside. So when I said free stream, that's a region which does not feel the effect of the solid plate, but there would be a region which is close to the plate where its experiences, or in other words, the presence of a solid boundary will exert some drag. It will retard that fluid motion. Okay, so that region which is retarded by by the solid plate, that's what you call as the boundary layer. Now, this boundary layer is very important, for example, in heat and mass transfer. So, either you might have learned or you might be learning that, you have situations where, either heat is going to get conducted from the solid plate to a nearby fluid, just like in a heat exchanger, okay. And that process, okay, so one of the ways of happening heat transfer is conduction. You could have as well as convection, which means it's determined by the fluid flow, right? So you would want to know, so here we have a typical situation where the fluid is very near to a solid. Let's say solid is at a different temperature from the fluid. You want to know how much is the heat transfer happening, and you would then really want to know what is the velocity profile, because it's not just due to conduction, but it is going to be convection as well. Okay, similarly you can have mass transfer also. For example, that's a solid, okay, and let's say it's dissolving into the fluid, or let's say some crystallization is happening. So there's going to be a mass transfer between the solid region and the fluid region. Again, the rate of mass transfer is going to depend upon how the fluid flow is behaving there. If the fluid flow is extremely slow, then diffusion is the only thing that will happen. But in general, you would want to, increase the speed of or rate of these processes. You would probably be, pumping fluids with sufficiently large velocity, and therefore there will be a boundary layer formation. And the mechanics in the boundary layer is actually going to determine how fast these transfer processes are going to take place. Okay, so that's one of the reasons why boundary layer is so much relevant to chemical engineers. So so there is a so this concept of boundary layer, okay, it happened, I mean the concept came up somewhere early 1900s, and this was done by a person, Prandtl. I think we heard this name sometime before, or you would have definitely heard Prandtl number by now, yeah. So so see, people were initially thinking about or let's talk about like this. So Reynolds number, right? Reynolds number is defined as the ratio of two forces. What are the two forces? Inertial by viscous forces. And people thought, okay, if we keep increasing the Reynolds number, then inertial forces are going to be much larger than viscous forces, right? Or we would think that, okay, the effect of viscosity becomes much smaller. We can actually neglect all the viscous effects, and we can only talk about just inertial effects. Or in other words, if you talk about Bernoulli's equation, right? Does Bernoulli's equation contain viscous effects, or you neglect viscous effects when you derive Bernoulli's equation? You neglect it, right? So you would think that if I am at a very high Reynolds number, I should be able to solve my fluid flow, okay, by just using Bernoulli's equation, and I can completely forget about the viscosity of the fluid, okay. So that was the initial thought. And then some of the experiments. So what they did is they looked at flow past body. So flow, let's say we will talk about flow past a cylinder. Okay, so if you have a cylinder and then fluid is approaching, and then it basically goes that way. Okay. So we now know that the solid is going to exert or let's talk about this. So the fluid is going to exert a force on the solid object. Okay, and that forces can have actually two components. Okay, a component that is parallel to the flow direction and a component that is perpendicular to the flow direction. So the component that is parallel to the flow direction is what we call as drag. Okay, the component that's perpendicular to the flow direction is typically called a lift force. And you know why the lift force is coming? Because that's typically the case when you talk about aeroplanes. Okay, and it's that lift force that helps you to fly the aeroplane. Okay, so that's where the origin is. So you typically you can talk about a drag force and a lift force. Now people thought, okay, we will calculate these forces. And when they try to come up with, try to compare experiments with Bernoulli's equation, they found that yes, they are able to predict lift forces very accurately, but not drag forces. Now we associate drag so much with viscous forces, okay, but we also say that, okay, if you keep increasing your Reynolds number, viscous effects should become lesser and lesser important, and therefore we should be able to predict that drag force just from Bernoulli's equation. But when they did experiments, the experiments never matched with the predictions from Bernoulli's equation. Okay, if you neglect viscous effects, the calculations were never correct. Okay, so then actually Prandtl came up with this idea of boundary layer. What he said is that however large Reynolds number is, there is going to be always a thin layer of fluid very near to the boundary where you cannot neglect viscous forces. So what he said is that even in this case, there is going to be a very thin layer near the solid region where you cannot neglect the viscous forces, and therefore you need to account for that particular mechanism, whatever is happening in that layer, to predict what is the viscous forces or really the drag force. Okay, and that's why Bernoulli's equation was not able to give you a good result for the drag force. So that's actually the origin of boundary layer. Okay, so the layer could be very thin. It was just like our roughness. Okay, you would think that roughness does not play any role, but roughness actually plays a major role. Similarly, here the boundary layer might be so thin, but it could actually be very important in determining what are the forces that are going to act on the particle. Okay, so that's where the origin of boundary layer has come from. And now, I mean, at various places you see this concept. Okay, you would think that the majority of the forces, okay, or the main mechanism that's going to be acted is something, but very near to something else, there could be a thin thing which you might generally tend to neglect, could actually be a very important thing. So it depends upon situations and so on. So people call all such things as boundary layer concept and so on. So this is why this is how the origin of boundary layer happened, and then of course then in heat transfer and mass transfer, everywhere you start seeing the importance of it. So that's the history. So let's look at so yeah, there are two things that we would be interested in this course. Okay, one is to see what is going to be the thickness of boundary layer. Okay, because that's the region where the fluid flow is seeing the solid plate. Okay, and then we want to, of course, not in this course, but you may want to talk about heat transfer across that layer and so on. So you want to calculate what is the thickness of the boundary layer. Second is that we will also use this concept to explain flow separation. So you remember in one of the classes I was talking about expanding sections and so on, and I said, yeah, the flow could get separated. Okay, so the analysis of boundary layer will actually tell you where does the flow separation happening or why does it happen, and so that's another thing that we are going to look for. And it's important to know whether flow separates or not, because that will also help you to determine how, whether the transfer process of heat and mass transfer are going to be affected or not. So these are the two aspects that we will look at. So we'll look at a very simple situation. Okay, we will only worry about a flat plate, nothing else. That's a flat plate, and we will say there is a fluid that's coming, okay, at a constant velocity. So the velocity profile is a constant, okay, and it's approaching the solid plate. And as soon as it approaches the solid plate, what would happen? The fluid element that's very close to, so the last one, okay, when it approaches there at this region, it's immediately going to be retarded by the solid plate. Okay, while everywhere else it's still going to be moving with, so let's call this a velocity u infinity. Okay, so the fluid is moving with a u infinity velocity, doubt? Okay, and then as soon as it touches the edge of that plate, okay, that fluid element is going to get slowed down, and then the next fluid element, and it keeps going, right? So if I look at if I draw the velocity, so up to here the velocity profile was flat, okay, or vertical. Immediately as soon as it touches, there will be a small region, let's say, I shouldn't draw this, there will be a small region where velocity would be, affected so much, and immediately after that it will regain its u infinity. So that's what is going to be the velocity profile. Okay, so that small region is where it is affected by the solid plate, and everywhere else the velocity is u infinity. Okay, but now as it goes downstream, as it proceeds further, even more and more layers are going to feel the effect of the solid plate, okay, because the solid is exerting the drag. So after a while, if you look at further downstream, you will see that it's something like that. Oops. Okay, so that much is the region which gets affected by the solid plate, and that will keep going. In other words, the thickness of this layer would keep expanding. Okay, so now it is even larger. Okay, so the thickness of this thing keeps expanding. So this is where we are going to define our boundary layer thickness. We want to define boundary layer thickness as the region which is affected by the solid plate. Okay, now in principle, all the fluid up to infinity will also see it. Okay, so if you look at the solid fluid here, okay, let's say this is the solid plate and the fluid layer, it gets slowed down and it really reaches, when it is really far. But we don't want to talk about that, so we need to give some criteria of telling what is the boundary layer thickness, and we can say that, let's say, whenever the velocity reaches 99% of the free stream velocity, we will call this as a boundary layer thickness, okay, or you could call it 99.99%, whatever you like. Okay, so we'll say that whenever the velocity is 99% of u infinity, we will call that as a boundary layer thickness. So if you mark that boundary layer thickness, so here you are starting from the edge, and then you're starting from the edge, and then it keeps increasing. Okay, so that's what the boundary layer is going to be. So that's just an imaginary surface that you have drawn to identify the boundary layer part of the fluid flow. So, yeah, so your interest is to find out what is that, right? So, typically we denote it with uh, uh, with delta, okay, as the thickness, and it turns out, which we will derive, delta of x. So, this is my x direction, delta of x, okay, delta at any place in x divided by x is approximately equal to 5 divided by square root of Rex. So, when I said Rex, the Reynolds number is defined based on the distance from the leading edge. Okay. So, typically we will define Reynolds number based on a given length scale. It could be the radius of the pipe or the size of the particle. Here there is no other length scale other than really the distance from the plate itself. Yeah. Does it decrease with x? So, let us see, delta of x basically is 5x divided by square root of x u infinity rho divided by mu. So, that is actually going as x to the power of half. So, it is increasing with why it increases. So, as we said, so as soon as the fluid touches the leading edge, okay, only that fluid particle that is touching the leading edge will experience the effect of the solid plate. Now, what is the problem with the guy who is just behind you? The only the fluid particle that is touching the leading edge will get retarded. Everywhere else, it's going to be still coming with that velocity of u infinity, right? But as it enters a little bit more, two of the layers will start experiencing it. Because this is so what is the solid plate doing? The solid plate is retarding the fluid motion, right? So it basically has to get transferred, right, across various layers. So here there is a fluid that's coming with a strong velocity. So only the fluid particle that's going to touch is going to be experiencing that. But then the next layer will see it, but a little downstream, and the next layer will see it a further downstream. So therefore the boundary layer will keep growing. Does that answer your question? Yes, yes, yes. Yes, you're right. So at the moment in this picture, I have assumed that the fluid outside the boundary layer is actually going all the way to infinity. Okay, so that's the only reason I have assumed that. Okay, but you are right that yes, the other region, the velocity will increase, and I'll point out that a little later also today. Any other question? Okay, so this is so for a laminar flow. Okay, if so, the flow field in the boundary layer could either be laminar or it could be turbulent. Okay, if the flow in the laminar in the boundary layer is laminar, then the thickness of the boundary layer is given by this expression delta of x by x is approximately equal to 1 by square root of Re. Okay, x where Reynolds number is defined based on the distance from the leading edge. Okay, and if you simplify that, you will find that the boundary layer thickness actually increases with x in a square root form. Okay. Now, what happens is that, oops. So, let us say that shows your growth of boundary layer. Okay. If the Reynolds number can get sufficiently large, okay, then even though the flow would be laminar at the near the leading edge of the plate, after a certain point, it will actually go turbulent. Okay, it can basically turn to a turbulent flow. So you would see that if you were to actually track the boundary layer thickness, you will see that it nicely, grow like a root X, and then suddenly there will be some point in which it will start, increasing suddenly. Okay, it will start increasing suddenly, and then again it will slow down. So what happens is that up to here, the flow would be laminar, and beyond that point, the flow would turn turbulent. Okay. Now, why that happens is not a part of this course, we can't say, but what is going to happen is that the layer in the boundary layer, okay, you already know that we have already talked about that, okay, that will constituted by 3 different parts. There will be a viscous sublayer very near to the wall, then there can be an overlap layer, and then there will be a turbulent boundary layer, and then there can be a free stream, okay. So, from here, what happens is that, so remember, so this region, okay, the region which is laminar, basically will become smaller and smaller and will become a very thin layer, which is what we called as the viscous sublayer or wall layer. And then there will be another region which is our overlap layer. And then we have our outer turbulent layer. And then outside is where we have our velocity as u infinity or the free stream velocity. So, this region, the delta by x is approximately going as 1 by square root of Rex. This region is where delta of x goes as Rex to the power of 1.5, much faster, and much downstream, delta by x goes as 1 by Rex to the power of 1 by 7, which is much weaker. Okay, so this is really the onset of transition. So this is the structure of the transition from laminar to turbulent layer, turbulent flow in a boundary layer. You want to clarify something? Ask us. Rex power 1.5, yes, yeah. So in the laminar, it's going to be root, okay, x to the power of half, or I have written it as delta by x is 1 by root of Rex. In the immediately after the onset, okay, it's going to be much faster. It's x to the power of 1.5, and then much further down it will be delta by x is 1 by Rex to the power 1 by 7. So delta will go as x by x to the power of 1 by 7. So it's x minus x to the power of 6 by 7, no? 1 minus 1 minus 1 by 7, yeah. So, yeah, so that's how the growth is going to be. What we are going to do now, oh yeah, let me then answer his question. So we have seen this before, okay, yeah. Correct. So we earlier we have looked at, somewhere there. Is much further downstream, okay. We never talked about the region which are very close to where the transition is happening. So it's really those 3 layers are formed and stabilized and so on. See, from the left, if you see, it's laminar. So it's not that at one point it turns turbulent, okay. It's the top actually that turns turbulent, and then the effects cascades down. So it basically takes a while for things to stabilize. Yeah, so it's just going to say that this boundary layer formation, okay, that's really what we talked also when we talked about entrance length. If you remember, in the first class, I might have spoken that if you have a channel, and if I say that if a fluid of constant velocity comes, okay, as soon as it touches the edge, it basically slows down, and then the region which is affected by that solid plate will grow like that. Okay, so inside this layer, so the fluid is, the velocity profile is going to be like this. So the regions which are very close to those plates, the velocity slow down, but in between the fluid is still coming with a velocity which is uniform, okay. uniform. Okay, so that is really basically the boundary layer growth. Okay, and whenever that fluid flow reach when the boundary layers actually merged, okay, beyond a point, so this will happen, and it will merge, and then after that we had everywhere in some sense boundary layer only. Okay, that's what we called as the fully developed flow. Okay, and that's what we analyzed and so on. And to answer your question, this is the region where you would see that. So if this was coming with a velocity of u infinity, okay, here this region and this region have slowed down. So that means this part of velocity field should be having a velocity larger than u infinity. In fact, you can use that mass conservation to calculate the velocity in that region. Okay, so this is what really boundary layer was in the context of what we had done earlier. What we are going to do now is try to derive an expression for boundary layer thick. Yeah. What is larger? Oh, so see, something is coming with a uniform velocity. Okay, the entire mass that is coming should go out, but part of it has retarded. That means the other part should get accelerated, right? Then only you can maintain the total flow rate. Otherwise, there is a mass loss, right? Or in. So as long as the fluid that's coming in has to go out, part is slowed down means part is sped up. Because the other parts have been slowed down. Yes, which would be actually in terms of pressure rather than anything else. So it's not that, so viscous forces are only going to anyway slow down. Or you can think about it as things are so fluid was coming, but it's getting squeezed, so it's actually speeding up. That's what really it is.